All right, the last topic in Chapter 10 has to do with determining what's called the percent yield of a reaction. It's basically just a measure of how efficient a chemical reaction is. The higher the percent yield, the better the reaction has run. And of course, not surprisingly, 100% yield is the best you can do. So if you get every single molecule or every single gram of material that it's possible to get, then you have 100% yield. This type of thing is very important in chemical companies. I worked for a number of years in the chemical industry before I got into teaching. And when you're making millions of pounds a year of various chemicals, even a 1% increase in 1,000,000 pounds of material, that's 10,000 pounds of extra product you have to sell. So chemists and chemical engineers spend a lot of time trying to get the percent yield in their reactions to be as high as it can possibly be. The first thing we need to know is the theoretical yield. The theoretical yield is what we've been calculating using stoichiometry. It's the maximum amount of the material that you can produce in your reaction. So every time we do a stoichiometry calculation, we're figuring out what's the best we could do. Now you also need to know the actual yield. The actual yield is essentially what you got when you ran the chemical reaction. And of course, the only way you can get the actual yield is to actually do it. You have to go into the lab or into the manufacturing plant, carry out the reaction, and simply weigh the amount of material that you ended up with. On a quiz or exam, I would always provide you with the actual yield. We can then calculate the percent yield by comparing the two. So the percent yield, as we said before, is simply a measure of how efficient a chemical reaction is. And we calculate that by looking at the actual yield and the theoretical yield. So the actual yield is what we got in the experiment. The theoretical yield is the best we could do, which we've calculated from stoichiometry, and then we simply multiply that by 100. So the best you can possibly get from a percent yield is 100%. If you get more than 100%, then that means you've done something wrong, because that would violate the law of conservation of mass. You can't get more out of a process than you put into the process. All right, let's work through a sample problem here. So in this reaction of aluminum and fluorine combining to form aluminum fluoride, we're starting out with 13.7 grams of fluorine. We have an excess of aluminum. That means we have more than enough aluminum to react with all of the fluorine. And I'm telling you that we got 17.6 grams of aluminum fluoride, which is our product. So that 17.6 grams, that is the actual yield. The theoretical yield, you're going to have to calculate using stoichiometry. So we're going to use the same unit plan that we always use for stoichiometry problems, and grams to moles to moles to grams. So we always start out with the material we're given. We know how much fluorine we have, and we're trying to find out the amount of aluminum fluoride. Because grams cannot relate directly to grams in a chemical equation, since chemical equations are based on moles. It's 2 moles of aluminum, 3 moles of fluorine, and 2 moles of aluminum fluoride. So for substances to communicate in a chemical reactions, they have to speak mole language. So the first thing we do is take our grams of fluorine and change it to moles. Then the moles of fluorine will be converted to moles of aluminum fluoride using the coefficients in the balanced equation, and then using the molar mass of aluminum fluoride, we can get back to grams. So we'll start out with our 13.7 grams of fluorine. Then using the molar mass of fluorine, which is 38 grams per mole, we change the grams to moles of fluorine. Then, looking at the balanced equation, we have 2 moles of aluminum fluoride produced for every 3 moles of fluorine, and then finally, we want to convert that back to grams. So adding up the molar mass of aluminum fluoride, we have 1 aluminum and 3 fluorines, that would be 84 grams, and that gives us the amount of aluminum fluoride we could expect to get from this reaction. So we would expect to get 20.2 grams of aluminum fluoride, and that would be the theoretical yield. That's the best we could possibly do. So if we want to calculate the percent yield, we need to compare the theoretical yield with the actual yield that was given in the problem. So as we said before, the percent yield is simply obtained by dividing the actual yield by the theoretical yield, multiplying that by 100. So we plug in our two numbers, multiply it by 100, and we get an 87% yield. Is that a good yield? It depends. In some reactions, 87% would be excellent. In other reactions, that would be terrible. It depends on the inherent efficiency. Some chemical reactions, if you got 50%, that would be phenomenal. And other reactions, if you got less than 90%, it would be terrible. So there's really no way to judge that. All right, let's see if we can put everything together that we've talked about in Chapter 10. So we want to calculate the theoretical yield, we want to figure out what the limiting reagent of a reaction is, and finally figure out the percent yield of a reaction. So this time we're going to be looking at the reaction of hexane and oxygen to produce carbon dioxide and water, so a basic combustion reaction. This time I'm going to give you amounts of both of the reactants, both the hexane and the oxygen. So 113.5 grams of hexane is combined with 351.2 grams of oxygen. One of those is going to run out first, and we want to figure out which one that is. Which one is the limiting reagent? The simplest way to do that is to simply start with each of these in a separate problem. So the first thing we'll do is figure out from 113.5 grams of hexane, how many grams of carbon dioxide could we get? Then we'll do a second calculation where we'll begin with our 351.2 grams of oxygen and figure out, in that case, how many grams of carbon dioxide we could get. Whichever one of those produces the smaller amount, that will be the limiting reagent. And that smaller amount will be our theoretical yield. And of course, to get the percent yield, you need the actual yield, which is also provided here. This is what we actually got. So your job is to figure out which of these two is going to give us the least amount of carbon dioxide, and that will be our theoretical yield. So let's start out with the hexane. We have 113.5 grams of hexane. We'll convert that to grams using the molar mass of hexane. And then using the balanced equation, we have 12 moles of CO2 produced for every 2 moles of hexane. And then finally, we want to convert that back to grams of CO2. Molar mass of CO2 is 44. And that tells us that we will get 348.4 grams of carbon dioxide in this reaction. That's the best we could do. However, we need to find out how much we can get from the oxygen. So this time we'll do a second calculation, but we'll begin with the grams of oxygen. Then using the molar mass of O2, we'll change that to moles of oxygen. Again, looking at the balanced chemical equation, we get 12 moles of CO2 for every 19 moles of O2, so that's our coefficients here. And then once again, we'll want to change moles of carbon dioxide into grams. And this time we get 305 grams of CO2. So it looks like the oxygen gave us a smaller amount of CO2 than the hexane did. And that means that our limiting reagent is the O2. Whichever substance produces the smaller amount of material, that is our limiting reagent. So our theoretical yield is however much you get from the limiting reagent, which would be our 300.5 grams. So the hexane in this particular case would be an excess reagent. We had enough hexane to get all the way to 348.4 grams, so we're going to end up with some leftover hexane at the end. As soon as we reach 305 grams of CO2, we've run out of oxygen, and so even though there's hexane left, there's really nothing we can do with it. So finally then, to get our percent yield, as we've talked about before, we divide the actual by the theoretical yield. So the 288.3 grams of actual yield divided by the 305 grams of theoretical yield, and we get a 94.5% yield.